In the last clip, we saw the O2 MO diagram. We saw that the MO diagram can be used to understand the two bonds in the O2 molecule, the sigma bond, the pi bond, the net four remaining pairs of non-bonds in the net average, and the magnetism of O2, that O2 is attracted to a magnetic field, it's paramagnetic. But we also, in the last clip, began introducing the concept of MO diagrams for central atom molecules. And central atom molecules are crucial to our understanding of the covalent bond. It forms the heart of VSEPR and of Lewis structures. So, in this clip, we will look at our first central atom molecule, and the molecule we pick is CO2. The procedure was outlined last time, and let's review what it is. In the central atom molecule, the central atom MO diagram, the central atom is on the left, the peripheral atoms are on the right. The central atom in CO2 is carbon. We're going to have an energy scale. We're going to draw the central atom AOs using this energy scale. And what are the atomic orbital energies? Which orbitals are lower in energy? Carbon or oxygen? Put it in chat, please. Carbon or oxygen, which are lower in energy for atomic orbitals? Oxygen is more electronegative. Oxygen orbitals are lower in energy. And which are lower in energy? 2s or 2p? Put it in chat. Which are lower, 2s or 2p? 2s is lower in energy. Well, the atomic orbital energies of the atoms of the elements are well known. We can look them up, and and I put them right here. It's exactly as we thought. The oxygen 2s is minus 32 EVs, lower than the carbon 2s of minus 21 EVs. The oxygen 2p is at minus 15 EVs, higher than the oxygen 2s, and it's lower than the carbon 2p at minus 11 EVs. And we now want to draw the central atom AOs. And so here I put them there. Remember, there's the carbon 2p at minus 11 EVs, all three of them, and the carbon 2s at minus 21. We now come to the very important concept of molecule geometry equivalent orbitals. Molecule geometry equivalent orbitals. And in the central atom molecule, the molecule geometry equivalent orbitals are on the peripheral atoms because the two O's in CO2 are similar to each other, and they're going to contribute molecule geometry equivalent orbitals. In the text that I wrote in the slide, I call them similar looking pairs. That means molecule geometry equivalent orbitals. The oxygen on one side, its 2s, looks just like the oxygen 2s on the other side. The oxygen 2p sigma just looks like the oxygen 2p sigma on the other side, the pi on the other side. And what is the rule with molecule geometry equivalent orbitals? Molecule geometry equivalent orbitals are always mixed first. And so we're going to mix first the 2s with the 2s. We're going to make the psi 1 and the psi 2. I'll give you a second to imagine it so that when you see the picture you can see if you got it right. And here it is. And notice that I have put them very close in energy. These two oxygens are not in bonding distance to each other. There's very little constructive or destructive overlap. They're too far apart to overlap. There they are, the psi 1 and psi 2. Now imagine in your mind the sigma psi 1 and psi 2. I'll give you a few seconds to imagine it, what it looks like, and you can check if you got it right. There it is. And they look on my diagram as far apart, but you see that bracket? That means they're actually very close in energy. I'm just saving room for drawing more orbitals. But you can see, there they are, psi 1 and psi 2. By the way, all these orbitals I'm drawing so far, are they bonding or non-bonding right now? Put it in chat. So far, all the orbitals I've drawn so far are non-bonding. The two oxygens are too far apart to make bonds or antibonds. We've done now the sigma. We have to look at the pi. Let's imagine what they look like. Remember, there's the pi that looks like this, and there's the pi that looks like this. And so there they are. And again, they're bracketed all close. They're very similar in energy. Maybe because there's some small amount of overlap, the ones that look slightly destructive are ever so slightly higher in energy. It's a difference of energy that will not matter. Good. We now have all the atomic orbitals, and we're on to the next step of the MO diagram. We want to mix in pairs the left and right sides. And remember, once we mix a pair, that pair will be used up. A bond is 200 to 400 kilojoules per mole. Put in chat, roughly in EVs, what's 200 to 400 kilojoules per mole, if you can remember. 200 to 400 kilojoules per mole is 2 to 4 EVs. So these orbitals are going to go up and down 2 to 4 EVs onto our diagram. But which ones are we going to mix? And that's what the important rules 5 and 6 are. We're going to mix orbitals which make the strongest bonds and antibonds first, and orbitals that are initially closest in energy to each other, they're the ones that mix best. We want to find orbitals closest in energy and to make good interactions. By the way, the best interactions will be sigma or pi. Put it in chat. Sigma. So there's a myriad of choices. Guess which orbital from the carbon makes the strongest bond and antibond with which orbital on the oxygen side, the peripheral side. I'll give you a few seconds to look. You can put it in the chat if you want. Look for ones that are close in energy. The carbon 2p is at minus 11 EVs. The oxygen 2p is at minus 15 EVs. They're very close in energy. They're the closest. And we're going to look at their sigma interaction. We'll make the psi1 and psi2. And I'll show them right here. But before I do that, we need to understand one last key point, which is in orange. At this point, this is the first time we're going to be mixing two orbitals of, I should switch my hands, two orbitals of different energy. The oxygen orbital is of lower energy, and the carbon orbital is of higher energy. And if I read what it says in orange in 6, resultant low or high energy mixtures resemble more initially the low or high energy orbitals. So this is the low energy one. It's going to make the bonding one by going down. This is the high energy one. It's going to make the anti-bonding. So the low one will make the bonding orbital. The initial high one will make the anti-bonding orbital. And I will then show them. I will lower the O2 peripheral orbital to make the bonding, and I will raise the higher carbon at AO to make the antibonding, and I'll show them right here. Oops, wrong place again. I'll show them right here. Oh yes, I drew the AO's lines here, and there they are. Now here's an interesting thing. Which one is psi1 of those two pictures? Which one is the addition of the two? Put it in chat. Is psi1 the high energy one or the low energy one? Look carefully at the picture, please. Put it in chat. Which one is psi1, the high energy one or the low energy one? Psi1 in this case is the high energy one. All that has you to do is you have to make psi1 and psi2. You have to add and subtract. But it turns out subtracting the two is the one that leads to constructive interference, because you can see that subtracting the two actually ends up putting constructive interference. Okay, that's our first pair. What's the next pair we should look at? And once we've used up a pair of orbitals, is used up. And sigma is always better than pi. And I guess the next best choice is the carbon 2s and, again, the oxygen 2p. And here I'm just going to show them. There they are. That's the psi1, which is the normal way, is in lower energy. And that's the psi2, which is in higher energy. And notice the psi1 is going down from the carbon, and the psi2 is going up from the oxygen, since carbon 2s is lower in energy. Okay, what else do we have? We've used up all the carbon orbitals. There were 4 carbon orbitals. Have we used up? No, we have, no, we haven't. Where did I get that from? We have the pi interaction. We can make bonding and antibonding. So we'll make the side one from the bonding, and we'll make the bonding pairs, and we can do it for both the ones that are like this and the one like this at the same time, and we can make the pi antibonding. There. Now we've used up all the carbon orbitals. The px, the py, the pz, and the 2s, they've all been used in the orbitals we just made. What's the next step? The next step is carry over remaining side orbitals to the diagram center. Oops. And so I do that right here. At this point, let's draw the tie lines. The tie lines, remember, are the lines that tell you where each orbital came from. And, I haven't drawn all. Which orbital haven't I drawn over yet? Yes. Do you see there are still 2 remaining p orbitals on the oxygen, which I haven't brought over? And there I have. They have nothing to interact with. They are not capable. They do not make sigma or pi bonds. Okay. So now I've drawn all the orbitals, and now I draw the tie lines. And notice that there's one tie line that's missing between the. But that's okay. These are the orbitals, and now we're going to start drawing horizontal lines with orbital energies. And we will fill these with electrons. So CO2 has 6 valence electrons on each oxygen, 4 electrons in the carbon. That's 16 filled orbitals, 16 electrons, and we'll just put them in right here. And we can just count. 2, 4, 6, 8, 10, 12, 14, 16. So those are the 16 electrons. And I remember, draw the orbitals that are unfilled as horizontal lines without electrons. What are the names of these orbitals? Let's start from the bottom. Do you remember that s orbitals are sigma-like or pi-like? Sigma. Are these sigma bonding, non-bonding, or anti-bonding? Put it in chat. The 2 at the bottom. They are too far apart to interact with the oxygen. They are non-bonding. So they're 2 sigma non-bonding orbitals. Next one up is sigma. Sigma bonding or bonding, non-bonding, or anti-bonding. It is sigma bonding. Next one up, sigma bonding. Then come 2 pi bonding. These 2 here, pi bonding, non-bonding, or anti-bonding. They're on the oxygens. There's nothing on the carbon. They are non-bonding. And they are non-bonding. And we have then, that's sigma star. Remember, anti-bonding is out of phase. These next 2 up here, what are they? They are pi star, they are antibonding, and finally we have sigma star. We can now look at the sigma bond order. The sigma bond order we have to count. Non-bonds don't count. Sigma bonds count for 1. The sigma bond order is, put it in chat, I'll give you some time. The sigma bond order is 2. There are 2 sigma bonds filled. What is the pi bond order? The pi bond order is, we filled 2 pi bonds. The pi bond order is 2. And what is the how many non-bonding pairs of electrons are left? Well, we have 4 non-bonding orbitals. There are 4 pairs left. Finally, we can look at the magnetism. Sorry. Before we look at the magnetism, let's draw the structure. We're going to draw 2 sigma bonds, 2 pi bonds, 4 remaining non-bonded electrons, which notice are all on, the non-bonding electrons are all on the oxygens. The lone pairs should go where? And we're going to draw 2 sigma bonds, 2 pi bonds between the atoms, and there they are. The Lewis structure exactly corresponds to the MO diagram. And finally, we can look at the question, is this paramagnetic or diamagnetic? Are there unpaired electrons or not? There are no unpaired electrons, and therefore the system is diamagnetic.